All right, let's talk about something every data scientist knows. That moment you have a model that works in your notebook, but getting it into the real world, that's a whole different beast. Today, we're going to bridge that gap. We're taking a model on the full journey, from a messy prototype to a rock-solid production system. Let's dive in.
So, you've got your prototype, right? It's probably a bit manual, maybe a little brittle. It basically lives and dies on your laptop. But then you have the dream, a fully automated, super reliable system that's plugged into everything. The gap between those two, it can feel like a chasm, but that's exactly what MLOps is for. It's the bridge.
So think of this whole process like we're taking a tour of a high-tech factory. First, we'll check out where the raw materials come in. That's our data and features. Then we'll head to the engine room where all the magic happens, training and evaluation. After that, we'll see the shipping department where we deploy the model. And we're not done. We'll stick around for post-sales support to make sure it stays reliable. Finally, we'll zoom out and see how it all fits together with something called the MLOps ladder.
Okay, first stop on our tour, the foundation. This is all about data and features. You can think of this as the factory's receiving dock. And you know the saying, right? Garbage in, garbage out. If our raw materials here aren't perfect, the final product is going to be a disaster. You know how we use Git to version our code, right? Well, what about our data? It changes all the time. That's exactly where data versioning comes in. With tools like DVC, that's data version control, we can essentially commit our data set. We can link a specific version of our data to a specific model training run. Why does this matter? Well, it means if your boss asks you to reproduce a result from 6 months ago, you can. You can pull the exact data it was trained on. It is absolutely the cornerstone of reproducibility.
So once we've cooked up all these amazing features, where do they live? We can't just have them scattered around. We need a single source of truth, and that, my friends, is a feature store. Think of it as a central library or a meticulously organized pantry. It stops that absolute nightmare scenario, where the training team calculates user activity one way, but the live prediction system, well, it does it a completely different way. That kind of inconsistency will silently kill your model's performance in the wild.
Okay, so consistency is huge. But there's an even sneakier, more dangerous problem hiding in our data, a real silent killer. How do we prevent our model from becoming a time traveler and accidentally learning from the future?
The answer is something called point-in-time correctness, and the rule is actually pretty simple, but it is so important. When we build our training dataset for any historical event, we can only use feature values that were known at that precise moment in time and not a second later. This stops the model from cheating by peeking into the future. Without this, you get these models that look amazing in testing, but are completely useless in reality because their performance was based on a lie.
All right, our raw materials are prepped and ready to go. Now we're heading to the heart of the factory, the engine room. This is the main assembly line. It's where we actually build the model and then run it through some serious quality assurance.
Now, before we just hit the big green train button, we have to tune a bunch of dials on the machine. These are called hyperparameters. They control how the model learns. Things like the learning rate, which is like the size of the steps it takes, or the max depth of our decision trees. And we don't just guess. We run tons of experiments to find the perfect settings. And we use tools like MLflow to keep a detailed logbook of every single experiment we run.
Okay, training's done. Now it's time for the model to get its report card. And I'm not talking about a single accuracy score. That can be really misleading. I'm talking about the confusion matrix. This gives us the full, detailed breakdown. It shows us exactly when we were right, our true positives and true negatives, and, way more importantly, how we were wrong, our false positives and false negatives.
Let's break that down. First up, precision. It answers one simple question. Of all the times we shouted yes, how often were we actually right? That's it. High precision means when our model makes a positive prediction, you can really trust it. It's not crying wolf. Recall, on the other hand, asks a different question. It asks, of all the yes cases that were really out there, how many did we manage to find? High recall is all about being comprehensive, about not missing anything important. And this is where that classic trade-off comes into play. Do you need your model to be super cautious and precise, or do you need it to cast a wide net and have high recall? So how do you balance that trade-off between precision and recall? Often, we want a single score to summarize the model's overall performance. That's where ROC-AUC comes in. It stands for area under the curve, and it basically measures how well the model can tell the difference between the positive and negative classes. A score of 1.0 is a perfect model. A score of 0.5? That's no better than flipping a coin. So obviously we're always shooting for as close to 1 as we can get.
Yes, the model passed quality control with flying colors. So, where to next? We're heading to the shipping department. It's time to package this thing up and get it out the doors so it can start doing its job in the real world.
This packaged model has a name. It's called a model artifact. Basically, we take our trained model and, through a process called serialization, we save it as a single file. This file has all the learned weights and parameters baked right in. For Python projects, we might use something simple like pickle. But if our model needs to run in different environments, like on a Java server or a mobile device, we'd use a universal format like ONX.
So how do we actually serve this artifact to users? We build a stack, kind of like stacking Lego blocks. The bottom layer is an API, something like FastAPI, which just creates a web endpoint for our model. Then we take that API and all its code and package it up into a neat little box called a Docker container. This box has everything it needs to run anywhere. And finally, the top layer is an orchestrator, usually Kubernetes. It's the master controller that manages all our containers, automatically scaling them when traffic gets heavy and making sure our service never goes down.
And just like that, our model is live. But wait, the job is absolutely not done, not even close. Welcome to the final and maybe most important part of our factory tour, long-term reliability and support. Just because the model is out there doesn't mean we can forget about it. The world changes, and we have to make sure our model changes with it.
And what's the #1 enemy of a model in production? It's something called data drift. This is when the real-world data being fed to your model starts to look different from the data it was trained on. Maybe customer behavior shifts, or a new competitor enters the market. The world doesn't stand still, and the model's understanding of it can silently become obsolete.
So how do we catch this drift? We use statistical tests to measure it. There are a few out there, but a really popular one for monitoring is the Population Stability Index, or PSI. And when it comes to PSI, there's one magic number, a critical threshold that you absolutely need to burn into your memory. And that number is 0.25. If you see a PSI score go above 0.25, alarm bells should be ringing. That's not a suggestion. It's a giant flashing red light. It means your data has shifted significantly and your model is now flying blind. It is an undeniable signal that you need to get back to the factory and retrain. But just knowing the model is performing well isn't always enough, right? We and our stakeholders need to trust it. We need to know why it's making the decisions it's making. This whole field is called explainability. And using amazing tools like SHAP or Lime, we can finally peek inside that so-called black box and understand exactly which features push to prediction one way or the other. This is crucial for debugging and building trust.
Okay, so we've seen all the different departments in our MLOps factory, from the receiving dock all the way through post-sales support. For our final stop, let's head up to the observation deck and look at the big picture, how all these pieces come together to define how mature your MLOps process really is.
And this is what it looks like. The MLOps ladder. Everyone starts at level 0. This is the Wild West. Completely manual, chaotic, held together with scripts and prayers. Then you graduate to level 1, where you've automated your ML pipeline. Nice. Level 2 is when you bring in CI/CD and automate the model deployment itself. But the holy grail, the top of the ladder, is level 3. This is full end-to-end automation, where the system is smart enough to detect drift and automatically trigger a retraining pipeline all on its own.
And that journey, right there, from manual chaos to a self-healing, fully automated system, that is the core promise of MLOps. So as we wrap up, I'll leave you with one final question to think about. Take a good, honest look at this ladder. Where does your project really stand today?